Hello everyone. In this video, we will talk about analyzing thin structures efficiently using Ansys Mechanical. We come across thin structures in engineering quite often, and analyzing such designs poses some challenges. In this video, we will address these challenges. In particular, we'll try to address three questions. What are thin structures and what is so special about them? Why should we use shell elements to model thin structures? And how to model thin structures using shell elements in Ansys Mechanical. Ready? Let's go. Structures whose thickness is significantly smaller than the other two dimensions are referred to as thin structures. There is no rule of thumb, but one guideline for designating a structure to be thin is when one dimension is 10 times smaller than the other dimensions. Many of the devices and equipments that we see in daily life can be categorized as thin structures. Some of the examples are electronic enclosures, pressure vessels, fuel tanks, etc. Ideally, solid elements should have an aspect ratio close to 1, but we can still obtain fairly accurate results at higher aspect ratios. However, if the aspect ratio is too high, which is often the case when meshing thin structures using solid elements, we begin to see poor results. The alternative is to generate a very fine mesh to achieve solid elements with reasonable aspect ratios. But that increases the number of degrees of freedom, which in turn makes it computationally very expensive. This is where the shell elements appeal as an efficient way of modeling thin structures. So what are shell elements? Shell elements are spatially 3D but geometrically 2D elements, meaning their thickness is not modeled explicitly. Instead, it's defined as a section property. Unlike the solid elements, each node of a shell element has 6 degrees of freedom, 3 translations along the principal axis and 3 rotations about the principal axis. The rotational degrees of freedom provide information on whether the cross-section in that location remains perpendicular to the midsurface or if it has rotated. Another key point for shell elements is that they have membrane and bending behavior. Membrane behavior being related to the in-plane deformation of its nodes, and bending behavior being related to the out-of-plane deformation of its nodes. For instance, if we consider sheet metal, we know that the membrane stiffness is much higher compared to the bending stiffness, since it's relatively easy to bend sheet metal compared to pulling it. We will discuss more on this when the results of bending and membrane stresses are evaluated. However, it may suffice to say for now that because of the assumptions related to its behavior, a shell element also has a state of plane stress. So it has zero stress in the direction of its thickness. This is a suitable assumption for thin structures, but it would not be valid for thick structures that could be compressed between its two surfaces. Therefore, in summary, we use membrane and bending behavior to capture the response of shell elements, but doing so does include an assumption that the shell is assumed to be thin and does not have a stress component in its thickness direction. Another important point to note is the element coordinate system for shell elements. By default, the orientation of the axes is defined based on the nodal connectivity. In the shell element shown here, with nodes I, J, K and L, the x-axis is parallel to the side ij, the z-axis is normal to the shell, which is determined using the right-hand thumb rule in the direction of the IJKL numbering, and the y-axis is created normal to the x and z axes. As a result, in some cases, The x and y axes may be oriented randomly, which may cause issues in interpreting results such as stresses that make more sense in local coordinate system. In such cases, one may align the element coordinate systems so the shell results are interpreted in its solution coordinate system. We'll discuss more about this during later part of the video. Let us now see how to model thin structures using shell elements in Ansys Mechanical. In Ansys Mechanical, thin structures are modeled using surface bodies. They are recognized using this symbol in the model tree. Surface bodies are geometrically 2D but spatially 3D. They can be created using SpaceClaim or they may be imported from external CAD systems in neutral file formats. In SpaceClaim, the surface bodies can be prepared from sketches, from solid bodies using midsurfacing, or from line bodies using the pull tool. Surface bodies have two key attributes, shell thickness and shell offset. Shell thickness can be specified in different ways. If you have used midsurfacing tool for generating the surface, then SpaceClaim carries forward the thickness information into Mechanical. If you have imported the surface from an external CAD file that does not carry this information, then you can define it manually. It is also possible to define variable thickness or layered sections with different thicknesses using these two objects under the geometry tree in Mechanical. The other attribute, shell offset, helps in identifying whether the surface represents the mid-surface, the top or bottom of the actual geometry. The default is that the surface and the corresponding mesh will represent the mid-surface, but one can change it to any location between the top and the bottom faces. Offset type can be chosen in the drop-down menu located in the Details view of a surface body. Surface bodies thus have a normal direction identified by a green coloring when the surface body face is selected. Shell elements have a top face and a bottom. Let us now proceed to demo how to use shell elements in Ansys Mechanical. In this workshop, we will use a model that has three parts, a pressurized cylinder and two supports that hold it. All parts are made of structural steel and the supports are connected to the cylinder via bonded contacts. The supports are constrained in the bottom using fixed supports and a pressure of 500 psi is applied to the inner surface of the cylinder to represent pressurized fluid. In this case, all the three parts are represented as solid bodies and second order tetrahedral elements are used to model them. If we look at the cross section of the cylinder, we notice that its thickness is much smaller than its length and its radius. So it may be treated as a thin structure and therefore it can be modeled using shell elements. Now let's see how to go about it in Ansys Mechanical. Go to Ansys Workbench, duplicate the current static structural system and rename the new system as thin structure. Now right-click on the geometry cell of the new system and choose Edit Geometry in SpaceClaim. Now we are in Ansys SpaceClaim. Go to the Prepare tab and click on Midsurface option. We need to select a pair of offset faces and SpaceClaim will replace the solid body with a surface midway between the two offset faces. If we wish the offset to be created along the thickness other than at midway, we may control that over here. Now SpaceClaim will save the thickness and the offset details between the two faces as a property of the surface body. This way, the solid bodies have now been replaced with 4 surface bodies. Since the vessel is now represented by 4 separate surface bodies, we need to connect them with each other. In this example, we do this using shared topology. This way, a conformal mesh is generated between the parts and the bodies are connected at nodal level. So select the 4 surface bodies in the tree outline by holding Ctrl key and clicking on them. Then go to the Workbench tab and click on the Share option. Notice that the edges are highlighted in blue, showing that Share topology has been activated along these edges. Close SpaceClaim, go back to Workbench window, right-click on the model cell of the thin structure system and choose Update. Double-click on the model cell to open the model in Ansys Mechanical. Now open Mechanical and let's expand the geometry. Notice that surface bodies are indicated using this symbol. When we click on the surface bodies, we see that material assignment is missing. So select all the 4 surface bodies by holding Shift and clicking on the first and last surface bodies. Click on Material Assignment in the Details window and choose Structural Steel. Now let's take a moment to go through the various properties of a surface body. First, note that the thickness of the tank body has not been modeled geometrically. Instead, it is defined as a property of the surface body under the details, which could also be manually entered or changed if desired. The shell offset is set to middle by default, but it can be changed to top, bottom, or anywhere in between by using the user-defined option. Next, we go to the mesh. Since we modified the geometry, the scoping under body sizing is lost. To fix this, select the 4 surface bodies that make up the tank and click Apply. This will define a size of 0.5 inches for the shell elements that will mesh the tank body. Right-click on Mesh and select Generate Mesh. The supports have been meshed with solid elements, while the tank body has been meshed with shell elements. Recall our discussion about element orientation for shell elements. As discussed before, the z-axis is always normal to the plane of the shell element, but the x and y-axes for different shell elements may not be aligned. To fix this, we define the element orientation for the shell elements. To do this, right-click on Geometry, Insert, Element Orientation. Make sure the Body Select option is active and choose the 4 surface bodies that make up the tank body and click Apply. Next, we must select the surfaces, the normal to which will define the z-axis. Activate the Face Select option and select the 12 surfaces that make up the tank. Then click Apply. Finally, we need to select the edges to which the element's x-axis will be parallel. Let's say we want the x-axis to be along the circumferential direction of this tank. Activate the Edge Select option and select these 4 edges. Now right-click on Element Orientation and choose Generate Orientations. We now see the local element orientations. Blue lines indicate the z-axes, which are always normal to the surface of the pressure tank. Red lines indicate the x-axes, which are aligned in the circumferential direction, and y-axes indicated by the green lines are normal to the local x and z-axes. Now, if we are looking for the circumferential stress, we can simply choose the stress in the elemental x direction. Next, let's take a look at the named selections. Again, due to the change in the geometry, some of these named selections have lost their scoping. So let's go to the named selection vessel pressure. Select the surfaces that make up the tank body and click on apply. Now the vessel pressure consists of the faces that make up the tank. The final step we need to do before running the model is defining contact between the tank and the two supports. Recall that we used shear topology in SpaceClaim among the 4 quarters of the tank surface model. However, we did not use shear topology between the tank and the two supports. This is because the tank is meshed with shell elements whose nodes have 6 degrees of freedom, while the supports are meshed with solid elements whose nodes have 3 degrees of freedom. Due to this mismatch in the number of degrees of freedom between the solid and shell elements, we cannot use shear topology to connect solid bodies and surface bodies. So let's go ahead and define bonded contacts between the tank and the two supports. Expand connections on the tree outline. Right-click on Contacts, Insert, Manual Contact Region. A bonded contact is created by default. Set the tank surface to be the contact side and the top surface of the support to be the target side. The displacements of the solid nodes need to be coupled with rotations of the shell nodes to ensure deformation compatibility. So go to Details of the bonded contact and under Advanced, set the formulation to MPC and the constraint type to Projected, Uncoupled U to Rotation. Repeat this procedure for the contact between the other support and the tank body. Next, let's ensure that the loads and boundary conditions are applied correctly. We have defined fixed support boundary condition on the lower surfaces of the supports, and since the support geometry was not altered, we don't need to modify this boundary condition. An important thing to note here is that when fixed support boundary condition is applied to nodes of solid elements, all 3 displacement components of those nodes are set to 0. But when fixed support condition is applied to nodes of shell elements, in addition to the displacements, the 3 rotational degrees of freedom are also set to 0. Next, we have a pressure boundary condition. In the previous model where the tank was modeled as a solid body, applying a positive pressure on the inner surface of the tank resulted in outward pressure such that the tank was expanding. But in this model, applying a positive pressure results in an inward pressure being applied such that the tank is getting compressed. So why does this happen? If we activate the face select option and select one of the faces of the tank, the outer side of the tank is colored green, but the inner side of the same surface is not. This means that the top surface of the tank lies on the outer side, while the bottom surface lies on the inner side of the tank. So a positive pressure implies pressure being applied in the negative z direction, which in turn results in inward compressive pressure. To reverse the direction of applied pressure, we change the sign of the pressure from positive to negative. Another thing to notice is that in the previous model, we applied the pressure on the inner surface of the tank. But in this model, we are applying the pressure on the mid surface, which has a larger area than the inner surface. So to apply the same force in both the cases, we need to scale the pressure accordingly. Let's go back to the previous model and note the surface area of the named selection vessel pressure. Now let's note the surface area for the same named selection in our current model. We use the two surface areas and the pressure from the previous model to get the correct pressure to be applied to the mid-surface in our current model. Let's go ahead and modify this value. So when using pressure boundary condition for shell elements, it's important to ensure that its direction and magnitude are both correct. Now let's insert some results of interest to be obtained, starting with deformation for all the bodies. Next, let's insert membrane and bending stresses. Note that these are special results which are available for bodies modeled using shell elements. Right-click on Solution, Insert, Stress, Bending Stress. Select the four surface bodies forming the tank and click Apply to scope them to the bending stress calculations. Similarly, right-click on Solution, Insert, Stress, Membrane Stress. Select the four surface bodies forming the tank and click Apply to scope them to the membrane stress calculations. We notice that there are question mark symbols on the bending and membrane stresses. This is because such details are not written to the results file by default to conserve the file sizes. In order to write them to the results file, go to Analysis Settings, Details, and under Output Controls, set General Miscellaneous to Yes. Note that this step needs to be done before solving the model. Now we are all set to solve this system. Right-click on Solution and click on Solve. Now that the model is solved, let's take a look at the results. First, let's look at the total deformation. When we animate the total deformation, we see the tank expanding due to outward pressure being applied on it. If we compare the contours and the maximum total deformation in this model with the total deformation contours of the previous model, we see that the two results are very close. So by modeling the tank as a surface body instead of a solid body, and meshing it by using shell elements instead of solid elements, we are able to capture the deformation accurately without having to use a large number of very small elements. Next, let's look at the membrane stress. Note that this is in the local 1, 1 direction, that is in the x direction of the element coordinate system. We can display the element coordinate system by right-clicking on Solution, Insert, Coordinate Systems, Elemental Triads. Here, the red lines indicate the elemental x-axis, which coordinates with the circumferential direction. So this membrane stress can also be interpreted as the circumferential or hoop stress. Next, let's look at the bending stress in the elemental x direction. We see that the bending stresses are much smaller as compared to the membrane stresses. Also note that pressurizing a vessel allows for large pressure loads because the membrane stiffness dominates it. However, if we subject it to other loads that may cause bending, then the vessel may not be able to resist those forces as much. This concludes the demo and brings us to the end of the video. Before we wrap up, let's summarize the key takeaway points. 1. Due to their topology, thin structures are efficiently modeled using shell elements, which are geometrically 2D but spatially 3D, with their thickness being defined as a section property. To accurately capture the characteristics of thin structures, the shell elements have both membrane and bending behavior in its formulation, with the membrane stiffness being much larger than the bending stiffness. A result of this formulation is that shell elements also use plane stress formulation, meaning that they assume the stress gradients across the thickness to be zero, so they do not account for compression through the thickness. This is a reasonable approximation to make regarding thin structures, but not for thicker structures. The nodes on shell elements have 6 degrees of freedom, unlike solid elements that have only 3 degrees of freedom. Therefore, it is recommended to not use shared topology between them. Instead, MPC-based bonded contacts are preferred in connecting solids with shells. Finally, shell elements output some special results such as membrane and bending stresses in the element or solution coordinate system. Because of the shell formulation, we can directly separate and understand the difference in membrane and bending stresses to see which mode of deformation dominates. Doing so for solid elements is a lot trickier and less straightforward. This concludes the video. Thank you for watching, and do visit ansys.com/courses to discover more useful learning resources.